In the previous few lectures, we discussed about how to extract a layer and how to visualize the output of a layer, including the final layer and the initial layers. Now, in the next few slides, we will be seeing what we can use those information for. So, one such scenario is a very interesting idea of extracting the patch in the image at which a particular layer or a particular channel in a layer is actually looking at. So I will make it very simple. So let's explain the algorithm first, and then we will kind of make it generic. So the first step is obviously to choose a layer, and within that layer, the next objective is to kind of choose a channel. So for example, if I choose the final layer in the ResNet, it will have 2048 channels, and out of that, I'm going to choose the 10th channel. But one good way to select a channel, if you are allowed to choose only a single channel, one good way is like you consider all the 2048 channels and see which channel is actually having the most high energy activation. So whichever channel is having the highest activation, you choose that channel. That's one good way to choose. But in this case, I've not done that. I've just randomly picked the 10th channel in the final convolutional layer of ResNet 101. So if you do that, how do you do that? You can actually kind of use that forward hook concept which I was explaining to you earlier. Okay, so once you do that and the forward hook is established, you just run many images through the network and record the values of that chosen channel using the forward hook. So once you have this, then what you need to actually do is you just need to see the activations, the maximal activations for each of those images, and then at that point you just you identify the point in the original image and then crop that region, maybe with a bounding box you crop that region in the image and see what's happening there. So here is an example. So these are the images I passed through with the 10th channel in the final convolutional layer as the chosen layer, and whatever that layer is observing when these images are passed are actually seen at the bottom. So this is basically some portion here on the image, and this one is actually observing the text in the image, and similarly and so on. So one interesting fact you can think of this one is, if I pass any image, this guy is actually looking at the text in the image. So in the entire image it is looking at the text. So if I pass another image with the text, it may be looking at the text in that image. So that kind of makes some sense to the activations and its physical significance. So just to summarize, what we are doing here is, instead of just seeing the weights or the activations as it is, we are trying to see what those activations are looking at in the original image. So one such way is trying to see which patch in the image is what your activation is looking at. So this is a code. I think no need to explain this again. You just choose the layer, choose the channel, and then put a hook on that, and you pass many images through it, then extract that output out, and then kind of uh, display it. Okay, and while we did that, there is another interesting concept which evolved over the years, which is known as saliency. Saliency is something like the sanity checking of your working, and one such work which kind of was pretty interesting is like, you take an image, then you mask certain regions of the image. For example, the gray values that you're seeing over here are masks which are purposefully put on the image. So what the process is, you kind of uh, move a window which is masking. So when you are here, you kind of cut this region from the image and then put the image for classification, and whatever classifying value, so you ignore this guy and this guy for a moment, you concentrate on here. So this point it classified as something that is measured here, and similarly this point, when you mask, it is classified as something, you measure it here. So if you run through the entire image, you get some map like this, and this is what we call a saliency via occlusion. And what this graph or the image actually represents is a very interesting fact. So what is actually showing is the high values, or the red values means the probability is correct, the blue values means the probability is incorrect. So what it shows then is, if I mask this region, then the image is kind of misclassified. It's not going to classify it as its true label Pomeranian. Similarly, this is kind of blue. So if I kind of masks the wheel, it is not going to predict it as car wheel, which is kind of expected. And here also, this is the breed which is known as Afghan hound. So if I mask this, it's going to give me false prediction. And what is the prediction when you mask, let's say the face is masked, so this is obviously false prediction, but what is it going to be predicted is actually shown here. If I mask this particular region in the image, basically near the eyes, is going to predict it as tennis ball. That is because there's a tennis ball here, right? If I kind of mask this region out, which is exactly this, then this ball is there, so it may be predicting it as the entire thing as tennis ball. What you see is outside this region, whatever you're seeing, wherever you put the mask in the image, it is still going to predict it as Pomeranian. And similarly here, this is interesting. So any of these regions, if you put a mask, it is going to predict it as a cab, which is kind of makes sense, because if you see here, it's a cab, right? So that's the thing. And similarly here, if I kind of put this mask here, it is going to predict it as something else, like Irish setter, motherboard, some fur coat, or whatever. So it's going to be doing that. So I hope you understood these two. Now this is nothing but the activation. So if I kind of take the layer 5 and see the strongest feature map in layer 5, just like forward hooking, by passing this image, it shows here. Here the color is kind of inverse. The blue means the strongest and the red means the weakest. So the strongest activation is actually looking at the face of the dog here, the Pomeranian here. And these are actually kind of the if you kind of put this guy into, you multiply these two at different images, it is what actually showing here. So this image corresponds to this, but others are neighborhood images in that sense. Similarly, you can see over here, interestingly, this guy is not at all looking at the wheel, it is looking at something else while predicting, so it may not be the right layer to look at, but it's looking at the text. Definitely that's what we're seeing over here. So this guy is a text looking activation. And similarly here, this is looking at the face and not really at the Afghan hound. So the approach is very simple. You mask regions in the image, slide the mask each time predicting the class, and that's what you see over here, and identify the regions which will miss the classify the most, right? So that's what actually the these two kind of tells you. So this is basically you checking the saliency through occlusion, because you are kind of masking out the regions in the image. Okay, so it's interesting, right? And there is another way to check for saliency also, that is basically the saliency via back propagation. So this is also interesting. So let's say the forward pass is very well known to you, but we can actually do a backward propagation and calculate gradients all the way up to the image. So how to do that? You enable the gradients in the image to be true, and then you forward pass once, and then you choose. So basically you have the classifier head here, and there are many predictions, right? So bird, cat, dog, and all. So let's say this is the bird prediction. So what you're going to do is you put all others as 0, only the bird one as 1, and then with this you do a back propagation back, so all the way back to the image. Okay, so once you have that, so you basically do the bird with respect to the image. So you have these gradients through the backward hook. Okay, so we discussed that you can put forward hook to get the activations, and you can put backward hook to get the gradients. So once you have this, you just take the absolute of this, because I'm not interested in the negative values. And then of course the color has 3 channels, the color image has 3 channels, so you took the max out of this. So this is going to give you something known as the saliency map, or the gradient saliency map via back propagation. So let me remove it and show you the approach here. So you do, so basically you kind of choose the class that you want to look at. In this case, maybe bird. If you're interested in dog, you can choose dog. Only thing is you need to enable the gradients for the image as well, and you completely back propagate to the image, and then you kind of take the absolute of that and then max of that, you get something like this. So the interesting aspect that you're seeing over here is like this, the highly activated regions is almost at the bird region, right? So that's something which is kind of interesting, and that actually tells you a few things. Of course, this is the code. The code is pretty simple. As I said, the gradient has to be enabled, and then you basically choose the class that you want to back propagate through. You do that, and then you take the absolute, then the max, that's it, and then display. And two things, as I said, just important. One is there is this high gradient region, so if you disturb them, your prediction is going to be affected, and that's actually interesting. And that's where the adversarial attacks and all of the images are actually looking at, because you want to create the minimal disturbance in the image, but at the same time you want to make the classifier fail, right? So you have to look at these high gradient regions. Another interesting thought process is like, can I use these gradients to come up with something like a self-supervised segmentation approach? Because anyway they are high, and it's kind of showing the back mask or the edges of the bird here. So can I use it for segmentation, particularly self supervised segmentation?